In 1869, Major John Wesley Powell of the Civil War led a scientific expedition down the Colorado River and through this very Grand Canyon. Powell and his crew traveled by boat. They marveled at the canyon's huge walls made of colorful sedimentary rocks. Powell was also a geologist. To him, the walls of the Grand Canyon provided evidence of Earth's long history. Before the 1800s, most scientists thought that Earth was only a few thousand years old. But by John Wesley Powell's time, developments in the science of geology had led many scientists to change their ideas about Earth's age and history. Geologic time grew from thousands of years to many millions of years. For Powell and other geologists today, one goal of geology is to interpret Earth's history. Geologists do this by studying the rocks in the crust, especially sedimentary rocks, like the one seen here. Together, these rocks make up the rock record of Earth's past. Powell and other geologists have identified three main ideas used to study Earth. 1. The rock record provides evidence of geological events and life forms of the past. 2. Processes observed on Earth also acted in the past. And 3. Earth is very old and has changed over geologic time. In the 1700s, scientist James Hutton wrote a book called The Theory of the Earth. In this book, he established the principle of uniformitarianism. This principle states that the physical, chemical, and biological laws that operate today have also operated in past geologic time. This means that we can use evidence from what is happening on Earth today to discover what has happened in the past. It's important to remember that in accepting this principle, that the rates of these geologic events are very, very slow. Although Earth may seem unchanging to us now, over millions, thousands of years, Earth is changing. Relative dating was discovered in the 1800s. Relative dating is the method that geologists use to put rocks in chronological order. If we're looking at this sedimentary rock layer right here, we could infer that these rocks down here had to have been laid down before these rocks up here were created. The law of superposition states just that. In an undeformed rock sequence of sedimentary rocks, each layer is older than the one above it and younger than the one below it. So our oldest rocks are down here on the bottom at layer A, and our youngest rocks are up here on layer F. A is older than B, B is older than C, C is older than D, D is older than E, E is older than F, and vice versa. F is younger than E, E is younger than C, C is younger than A. We also have the principle of original horizontality. This principle states that layers of sediment are usually deposited in horizontal positions laid down flat. If they're tilted or bent, they must have been moved after deposition. So this rock layer right here, we can see all these folds and tilts in it. The principle of original horizontality says that these layers were placed down flat, and then because of some geologic event, they got tilted or folded into this position. Some typical geologic events that tilt or fold rocks would be if the rocks are at a fault zone, like the San Andreas Fault, and there's an earthquake, the rock layers might get tilted during mountain building processes. So a lot of plate tectonics activity will change rocks from their original horizontal state. Later geologists developed another principle used in relative dating. The principle of cross-cutting relationship states that when a fault cuts through rock layers, or when magma intrudes other rocks and hardens, the fault or intrusion is younger than the rocks around it. For example, in these pictures down here, we're going to start with the one on the left. D is an igneous intrusion that cuts through layers C, B, and A. D, therefore, must be younger than layers C, B, and A. If this igneous intrusion stopped right here on layer B, then we would know that the igneous intrusion is only younger than C and B. We would not be able to infer anything about A. Likewise, with this E right here, a fault, we can infer that E happened after or is younger than the igneous intrusion when C was formed, when B was formed, and when A was formed, because it cuts through all of these layers. Similarly, over in this photo, D is younger than C, younger than B, and younger than A. And E had to have happened after D formed because it cuts through it. The last thing that we're going to talk about today about reading the rock record is unconformities. An unconformity is an area where or surface that represents a break in the rock record. So deposition or rocks laying down has stopped for a long period of time, and then weathering and erosion has removed previously formed rock, and then deposition will resume. If we look at this picture down here, this area right here would be an area where deposition has stopped for a long period of time, and weathering and erosion have removed all of the rock that was once here. After millions and millions of years, deposition will continue and new rock layers will be laid down right here. There's three main types of unconformities that we're going to talk about today. Firstly, an angular unconformity. An angular unconformity happens when layers of sedimentary rock form over older sedimentary rock layers that are tilted or folded. So this is a picture of an angular unconformity. There's space in your notes to draw what an angular unconformity looks like. So to draw this, we're going to draw some layers that are angled, and then new sedimentary rock layer coming over it. Angular unconformities happen when rocks are folded or tilted due to fault zones or plate tectonic activity. The second type of unconformity that we're going to talk about is a disconformity. In a disconformity, two sedimentary rock layers are separated by an erosional surface. Because the rocks on both sides of the unconformity are of the same type, disconformities can be difficult to recognize. In this disconformity, or this picture, right here would be our disconformity. So there's erosional surface right here. It's not following the principle of original horizontality, which says the rock layers are going to be deposited in horizontal layers. This would be our disconformity. And the third and final type of unconformity that we're going to talk about is a nonconformity. In a nonconformity, an erosional surface separates older metamorphic or igneous rocks from younger sedimentary rocks. So I have a picture of both types right here. We'll start with the igneous rock. We have our igneous rock, or it could be an igneous intrusion, following the law of cross-cutting relationships. Says that this rock right here is younger than all the sedimentary rock layers around it. And the surface right here that separates the two would be our nonconformity. And on this picture over here, down here would be our metamorphic rock. And then this layer right here is our nonconformity, where the surface has eroded from the metamorphic rock, and now we have sedimentary rock layers on the top. If you're using the guided notes for this section, please fill in and answer the 3 conclusion questions. If you're taking your own notes, please write a summary at the end that includes the answers to these 3 questions. 1. Why does superposition apply primarily to sedimentary rocks? 2. How are cross-cutting relationships used in relative dating? And 3. How do unconformities form?